It's my pleasure to introduce Jiankun Sun. Jiankun is one of my former students, and I always think one of the pleasures of being in academia is to have what I call academic children. And there's an interesting thing about academic children is that the generations move much more quickly than my regular children. So I actually have the joy of working with former students who then become co-committee members with my new students. And that's what has happened here. So one of my other students is Dennis Zhang, who's now at WashU at Olin Business School. And he's also been on the committee together with me. And Jiankun has graduated now a few years ago. She is at Imperial College Business School. She will be joining us remotely. She will give the talk remotely. This is kind of exciting work. I've always been interested in the interaction of people with machines and computers. And this is a work about how we will try to include how people react with the algorithms that we use to prescribe kind of actions. So it's my pleasure, Jiankun, good seeing you. To introduce you, you go ahead. Thank you.
Thank you very much. Thank you. Hi, everyone. I'm Jiankun Sun from Imperial College London. Thank you for the invitation, and also thank all the audience here. So today I would like to introduce our research, which studied common problem in the application of smart algorithms in supply chain management. That is, the users may deviate from the prescriptions of the algorithms when they implement the prescriptions of the algorithms. So in this study, we examined the impact of such deviations and designed an algorithm that used machine learning techniques to predict such deviations, and then use the deviations to adjust the algorithmic prescriptions. And then we conducted a large-scale field experiment to show that our new algorithm could indeed reduce the deviations, improve the productivity, and also generate economic value. So this is joint work with Dennis Zhang, Haoyuan Hu from Alibaba Group, and also my advisor, Yang Megan. We performed this study at Alibaba Group, which is the largest e-commerce and online retailing platform in China. So Alibaba Group has a logistic affiliate called Cainiao Network. So we actually collaborated with the artificial intelligence department of Cainiao Network in this study. So this department designs all the smart algorithms for all kinds of operational decisions in its logistics business. When I worked in this department, actually, just to help understand how well the smart algorithms our department designed performed in practice, and how the workers actually feel about our smart algorithms. We actually spent a whole day working in the warehouse as a picking worker and also the packer. So this is just a video showing that I'm working as a novice packer, just learning how to just pack a package and all the operations in this packing process. So it's really a fun experience, and also learn a lot from this. So one important lesson I learned from this process is that the workers may not actually follow the prescriptions of the algorithms in the warehouse operations. So in the packing process, the workers may not actually use the prescribed box sizes given by our smart algorithm. So here's another video showing one of such case. So this worker was actually packing 2 boxes of one. Okay, 2 just a regular shaped boxes just into a single package. So now the worker was adding some extra wrapping around it. It's liquid and fragile. She tried to fit the 2 boxes in the prescribed box size, but she could not do that. So she just dropped the original box and turned to a larger one. Now she tried again. Still, it was kind of difficult for her to fit the 2 boxes in. Now, another worker came to help and say, well, you really need to arrange the items this way in the box. Okay, now she's good to go. But you can see that she ended up using a box that was larger than the originally prescribed box size. Okay, so actually you can see that these kind of problems will commonly exist in many contexts in the human AI collaboration. Actually, according to a survey by Deloitte Insights, many organizations nowadays still view AI as a tool to assist the workers rather than to replace the workers. So we can expect that in quite a long time, such kind of human AI collaboration will play a very important role in many operations contexts. Okay, so the bean packing process is just an example of such human AI collaboration. The AI decides the proper box size, and the human just use the prescribed box size to pack the package. But this is not unique in the bean packing process. It also exists in many other operations processes like put away, picking, vehicle routing process, and maybe also some other processes in warehousing and logistics operations. So, but you can see that when it is the case that the algorithm makes the decisions, and the human implement the decisions, then we might see some deviations in this process. Okay, we have seen this in the bean packing process, but it may also exist in many other processes. But when we design the algorithm, we typically kind of ignore such deviations. We just assume that the algorithms can give the final solution, and the human will just implement the final solution exactly. Okay, but as we have seen, this is not the case, and such deviations or such inconsistency between the prescribed prescriptions and the implemented solutions will impact the performance of the algorithm in practice. Okay, so this leads to our research questions. We want to understand whether workers actually deviate from algorithmic prescriptions and how such deviations impact cost and productivity. And besides, can we design a human-centric algorithm to reduce the deviations and improve productivity? And if so, what is the economic impact? So these are our research questions in this project. There has been a large number of literature about bean packing. Most of them focus on the designing the efficient algorithms to solve bean packing problem, which is a very classical optimization problem. But most of these literature mainly so they do not account for the potential behavioral deviations of the workers, but such deviations have been observed in many other processes like the task sequence ordering, contract decisions, and picking process, and also some other operational processes. And some literature also tried to propose solutions to such discretionary behavioral deviations. For example, some propose that we can have some interventions in the workflow management, or we could incorporate behavioral aspects into the algorithmic prescriptions. Okay, so our work contributes to the literature in three aspects. First, we demonstrate the existence of different types of deviations in a single operational process. And second, we propose a low-cost method for the deviations, for the deviation problems in the operational process. And finally, we also provide a causal assessment of the performance of our algorithm and show its practical improvement to reduce deviations and improve the productivity in practice. So we studied this kind of problem in the bean packing process. As I mentioned, the bean packing problem has been a very classical optimization problem. It basically says that given a set of items and a set of bean sizes, we would like to decide the right bean sizes and the right number of each bean size to pack these items so that the total number of beans and the total cost of beans could be minimized. Okay, and this is a kind of a brief description of Alibaba's bean packing algorithm when we conducted this research. So it's basically a nested heuristic optimization algorithm. So the first optimize the item positions and orientations, and then they optimize the box sizes, and finally they optimize the item packing sequence. They have a heuristic optimization algorithm for each part, and the three algorithms are basically hierarchically structured or kind of nested. So one feature I would like to highlight for Alibaba's original algorithm was that they set the maximum box fill rate to be 100%. So the box fill rate is the ratio of the total volume of the items to the box volume. Okay, so you can see if the box fill rate is 100%, it means that the total volume of the items in the box could be just exactly equal to the box volume. So the box could be really, really full of items. So later you will see that this is an important parameter in our research. Okay, so usually this algorithm works very well, but the workers may also deviate from the prescribed box sizes. So first, we want to understand why the workers may deviate in general. So we classify the deviations into two types, which we call information deviation and complexity deviation. So for information deviation, it means the prescriptions, the algorithmic prescriptions are infeasible or suboptimal, but the workers or the human actually implement some feasible and improved solutions. So this is usually because the workers or the users may have more objective information than the algorithm. For example, store managers may adjust the inventory decisions given by the inventory management system just because they have more accurate observations of the inventory records in their stores. So in this case, they have some information advantage over the algorithm, and thus the human can make better decisions than the prescriptions. So they deviate in this case. And in the contrast, complexity deviations are the cases where the prescriptions given by the algorithm are actually feasible and optimal, but human reverse to implement some suboptimal and maybe simpler solutions. So this is usually because the prescriptions are too complex so that the workers fail to trust, understand, or execute these solutions. Okay, so an example for this is that the dispatchers may deviate from the prescribed vehicle routing plans because they just prefer some visually attractive routes. So this is what we actually see at Alibaba Group. Sometimes the dispatchers, when they have just to check the vehicle routing plans, they say, oh, I do not think this is a good idea. I just prefer some other kind of plans, and I will choose to deviate from your prescriptions. Okay, so these are two types of deviations in general. So now we want to check the historical data, historical bean packing data to investigate the deviations in the bean packing process. So we use the data of more than 1 million packages from 4 warehouses from Alibaba Group. And we find that there are 2 types of deviations. So for 1.6% of all the packages, the workers switch to smaller boxes. So these are mostly information deviation, because in these cases, the workers can fold the items or compress the items, or they find that the items could be aligned along the diagonal in the box. So in these cases, they find that they can actually use a smaller box to pack the items. But it's more frequently for them to switch to larger boxes, and the frequency is about 4.2%. So in these cases, for the cases switching to larger boxes, both information deviation and complexity deviation can exist. So we have some empirical evidence to support this. First, we find that the packages that contain an item that consistently causes workers to switch to larger boxes only account for less than 0.5% for all the among all the packages where workers switch to larger boxes. So this indicates that there is some information deviation because some items consistently cause workers to switch, but the ratio is very small, so it does not tell all the story. At the same time, we also find that in more than 1/3 of the packages where workers switch to larger boxes, the workers use boxes that are actually at least 2 sizes larger than prescribed. So 2 sizes larger is usually much larger than necessary if it's simply because the items are just slightly larger than expected or for some other reasons, for the information deviation reasons. 2 sizes larger are usually much larger than necessary. So this kind of indicates some complexity deviation. The workers may just grab some boxes just large enough to pack all the items in their view. And we also find that the workers are more likely to switch to larger boxes when tasks are more complex. For example, if the packages contain more than 1 item, or the prescribed fill rate is relatively high. So in either case, we find that the rate of switching to larger boxes are relatively higher. So this also indicates the existence of complexity deviation. Okay. All right. Okay. So sorry. Something. Okay. So now we look into the impact of these deviations on the box material use and the packing time. So again, we use the same data as in the previous slide, and we analyze the impact of the 2 types of deviations on the box surface area and packing time. And here are our major findings. First, we find that deviations overall increase the box cost and hurt the productivity. And second, we find that switching to larger boxes has more negative impact than switching to smaller boxes, because switching to larger boxes definitely increase the box material cost, and it also increases the packing time more than switching to smaller boxes. Okay, so given these findings, we decide our basic idea for designing the new algorithm, that is to recommend larger boxes when the workers are more likely to switch to larger boxes. So we focus on the cases of switching to larger boxes for 2 reasons. First, because they're more frequent and has more negative impact. And another reason is that if we focus on the switching to larger boxes, some simple interventions like just reducing the complexity by lowering the box fill rate may be effective, as we will see later in our design of the algorithm. Okay, so in our new algorithm, the first step is to predict the deviations to larger boxes. So we formulate this problem as a binary classification problem where we want to classify whether a worker will or will not switch to a larger box. Okay, so to identify this, we use machine learning techniques, and we have 43 features in our prediction. So they include the prescribed box fill rate, the package features, for example, the item dimensions in the package, and also the box features, for example, size of the boxes and the box size switching history of the box sizes. And we also use the data of 4 warehouses of Alibaba Group, and we split them into the training and testing set. And we try different machine learning models, and we find that the gradient boosted decision tree has the best performance in terms of its AUC value. So AUC value is a common measure of the performance of classification model in machine learning, and a larger AUC value usually indicates a better performance of the classifier. So in our case, the GBDT model has the best performance. And then with the model trained, then given a package and a prescribed box size, the model can output a prediction score, which can be viewed as the predicted probability of a worker switching to a larger box. So in this case, we just label that if the prediction score is larger than or equal to 0.5, we just label that the worker will switch to a larger box. And if the prediction score is smaller than 0.5, then we label it as the worker will not switch to a larger box. And our GBDT model can also output the importance of each feature in the prediction task. So here we list the most important 5 features in our prediction. And we find that some of the features relate to complexity. For example, the prescribed box fill rate and the total volume of the items. So these features kind of relate to complexity, which indicates the existence of complexity deviations. While other features are more kind of item specific, for example, the rate of switching to larger boxes corresponding to a specific item in the box. So these kind of features indicates the existence of complexity deviation. And now with the prediction model developed, we can develop the entire new human-centric bin packing algorithm. So here is our new algorithm design. So first, given the set of items and the set of bin sizes, we first run Alibaba's original bin packing algorithm. And in the same time, we also, and when we get to the prescribed box size, we input the prescribed box size and the item information into our GBDT model and get the prediction score. So in most cases, the prediction score will be larger than or equal to 0.5. So in these cases, we just output Alibaba's original prescribed box size. But for those cases where the score is larger than or equal to 0.5, what we do is we rerun Alibaba's original algorithm, but we set the maximum box fill rate to be 0.7. Okay, so you can expect that in this case, some of the packages will get a new prescribed box size that will be larger than the originally prescribed box size. Okay, but for some other but for some other packages, we will still get Alibaba's original prescribed box size because their original fill rate may be smaller than 0.7. Okay, so you can see that our algorithm only impacts those packages with a predicted score larger than or equal to 0.5. So our analysis later will also focus on these, what we call targeted packages. So to evaluate the performance of our new algorithm, we run a field experiment for 2 weeks in 4 warehouses of Alibaba's logistic network. And we randomly split the orders in each warehouse into 2 groups. So for the packages with the prediction score smaller than 0.5, we just output the Alibaba's original prescribed box sizes for both the treatment and control group. But for those targeted packages with prediction score greater than or equal to 0.5, in the control group, we just output Alibaba's original solution. But in the treatment group, we will run our new algorithm, and thus for some of these packages, they will get an adjusted solution which has a prescribed box size larger than Alibaba's solution. But some other packages in this group will still get Alibaba's original solution. Okay, so our analysis will just focus on these packages with prediction score greater than or equal to 0.5, which we call targeted packages. And we first run a randomization check to ensure that the 2 groups are well balanced in the important characteristics, including the number of items, volume of items, and weight of items. So this is to ensure that all the differences we observe in the outcome variables could be attributed to the difference in the bin packing algorithms in the 2 groups. Okay. So here are our major results. First, we find that our new algorithm reduces the rate of switching to larger boxes by 5.7 percentage points, which corresponds to a relative improvement of 19%. So this indicates that our algorithm indeed increased the conformance rate and reduced the deviation. And second, our algorithm improves the productivity by reducing the packing time by 3.2 seconds, which corresponds to an improvement of 4.5%. And third, we find that our new algorithm does not significantly increase the box material cost. Okay. And we also perform the OLS regression analysis, which includes the fixed effects of warehouse and days, and also include some other control variables to analyze the treatment effects of our experiment, and our results, the main results qualitatively remain. Besides, we also investigate where the gains of our new algorithm come from, and we find that the gains of our new algorithm mostly result from the reduction in complexity deviations. First, we find that the results, our treatment effects do not change qualitatively if we only focus on the packages which do not contain the items that always cause deviations to larger boxes. That is, if we exclude the cases related to information deviation, our treatment effect is still quite significant. And second, we find that the rate of switching to boxes at least 2 sizes larger than prescribed is also significantly reduced, because these cases are mostly related to complexity deviation. So it means that our algorithm has a significant impact on reducing the complexity deviations. And we also find that our treatment effects are significant on packages with more than one item, but not significant on packages with only one item. So this is another piece of evidence showing that the gains of our algorithm mostly comes from reduction in complexity deviations. And we also leverage the experiment as an instrumental variable to help us causally identify the impact of deviations on productivity. And our analysis showed that such deviations indeed causes an increase in packing time and thus loss in productivity. And finally, we use all our estimates earlier to estimate the potential economic impact of our human-centric algorithm. And we find that the savings of our new algorithm in labor cost can outweigh other potential cost increase in this process. And given the number of packages Alibaba processes every day, we estimate that the annual economic value of our algorithm for Alibaba could be $2.6 million, which is quite a significant number. So the number here is just an estimate, but what we would like to highlight is that by incorporating humans' behavior into our algorithm design, we could indeed generate significant economic value for the company, not only in the bin packing process, but this could also be potentially extended to some other cases. So to summarize, in this research, we find that the deviation in the bin packing process can increase the box material cost and lower the productivity of the workers. And we propose a human-centric algorithm design that learn and predict humans' deviations and use the predictions to adjust the algorithmic prescriptions. And we find that our new algorithm can significantly lower the deviation rate and also reduce the packing time significantly. And what we like to highlight is that the importance of integrating behavioral components with the optimization algorithm design, and because they could improve the realized performance of our algorithms in practice. So this concludes my talk. Thank you very much, and be happy to answer any questions. Thank you. Okay, I just noticed some questions here. First, why did we use the value 0.7 for fill rate? Why not 0.8 or something else? So that's a very good question. So 0.7 is a number that we discuss with the algorithm engineering team, because we want to carefully decide this number, because our prediction model is not 100% accurate. So we want to find a kind of a right number, so that we do not, for those packages where we originally recommend the right size, we do not recommend a larger size for these cases. So we want to avoid these cases. On the one hand, we want to reduce the number of kind of false positives on this side, and on the other hand, we also want to ensure that we can actually increase the box sizes for those true positives as many as possible. So 0.7 is kind of a number that kind of balances these two sides after our discussion with the algorithm engineering team. But given that, we could also use some other numbers here. So our results here could be kind of viewed as a lower bound of the potential benefits of such kind of design of the algorithm. So if we choose some other numbers, we might choose a better number. If we just try to optimize this number, we might have some better performance. Okay. Can we adjust the solution just using changing the fill rate? So the answer is not really, because so the prescribed fill rate is, as you can see, as I showed earlier, is an important parameter. It's an important feature to classify whether a worker will or will not switch to larger boxes, but it's not the unique feature that can very well identify these two cases. So we do need these machine learning techniques, the machine learning model, to predict whether a worker will or will not switch to larger boxes. And we cannot simply adjust the fill rate to achieve this, because in many cases, for many packages, even if the fill rate is really very high, we still have a large number of packages that the workers just use the prescribed box size. So we cannot simply just adjust the fill rate to change the box size, because that will kind of lead to too many kind of false positives, or just lead to many unnecessary changes in the box size.
Sorry, we have some questions from the live audience too. If I can hand the mic over, and a few folks here will ask you some questions.
Oh, sure. Sorry, I thought that I should first go over the QA and yeah, sorry.
No problem.
Okay.
Hi, Jiankun. So I had a question about the human level data, which I guess you probably don't have. It seems to me like a rookie, your first month on a job, you're going to deviate from the algorithm a lot more than if it's your 5th year in a job. There should be some element of learning, and I assume if you had that data, you would have included it, but can you comment anything in this dimension?
Yeah, that's a very, very good point. Actually, you're absolutely right. This is exactly what we observe in the warehouse. The new workers, they're not quite good at the packing tasks, so they may constantly deviate. But the more experienced workers can do this better. So the deviation rate is indeed related to the experience of workers. But just in our experiment, in our algorithm design and experiment, we did not account for this, because in their current operational process, the packing tasks are randomly assigned to the workers. So when we run the bin packing algorithm, we do not know whether a novice or an experienced worker will get this packing task. So we cannot use this in our prediction in our prediction and the new algorithm design. And in our experiment, as the pecking taxes are purely randomly assigned to different workers, that does not impact our estimate of the treatment effects. But I do agree that if you have this data, it can be incorporated into the algorithm design and potentially improve the performance of our new algorithm. Yeah.
So thank you for your presentation. So my question is, so you have basically two different models. One is the optimization model from Alibaba itself, and one is your machine learning model of your research. Do you see any future direction of your research that merges these two into one algorithm, given that you found the future importance in your machine learning algorithm and creating a model-based reinforcement learning could realize this thought?
Thank you very much. That's a very good point. Yes, in our model, in our case, we kind of separate this. We first do the prediction, and then we just kind of refer to the predictions results, and then we decide which how we adjust the parameters in the optimization algorithm. In the future, I do think that there might be some other way to kind of model this and maybe integrate them. So as far as I know, so they have done kind of this work in their new algorithm design. They actually use some deep reinforcement learning to figure out the optimal solution, and also they have kind of incorporate some of the behavioral aspects into their algorithm design. Maybe not using machine learning, but by just hard coding some of the rules or some other constraints in the optimization algorithm. So I do think there are some other possibilities for designing these algorithms, and our research just to propose one of such possibilities. Yeah.
Thank you, Jiankun. To the audience, we will take a 15-minute coffee break for those that are here, and whoever is on Zoom, feel free to do the same. So we reconvene in 15 minutes. Thank you very much. Thank you, Jiankun.
Thank you all. Thank you.